Chris Hooley is going to give the second talk of today. Chris is a lecturer in physics here at St Andrews, and his research is primarily concerned with trying to understand how, if you like, macroscopic properties of matter arise from the underlying quantum mechanics that's supposed to describe the world. Today, well, I hope that's okay. Today, Chris will talk to us about quantum mechanics and causality. So I'll hand over to him.
So, thank you very much for the invitation to speak at this extremely interesting meeting. I'm a little bit of an imposter. I mean, maybe we're all little bits of imposters. I have deep in my background some philosophical training, and I can use these words, but I am basically a physicist. Other speakers would say at this point, treat me gently. Actually, please treat me roughly. I mean, the point of this conference is that the physicists should get it going over, right? So I'm going to expose myself to that going over, and feel free to dig in. I've noticed that philosophers, when giving talks, often don't use PowerPoint slides, but do read a paper that they've written in advance. And physicists, when giving talks, often use slides, but extemporize the verbal accompaniment. I thought this was a perfect opportunity to take what I think is the best of both worlds, so there will be no slides and no red paper. I have some handwritten notes prepared a certain number of hours ago, and I'll be happy to share the contents of those notes with anyone who wants them afterwards, but obviously I'm also going to do so during. I also, although this creates a chairing nightmare, am very happy to take questions as we go along, particularly because some of this talk is going to be verbal and hand-waving, literally, explanation of what I think is a key experiment in understanding quantum physics and causality. And if you don't understand what I'm saying about the experiment, we'd better clear that up at the point where I'm describing the experiment. So please don't hesitate. If I say something that you don't understand at that point, just stick your hand up. Don't wait till the end. That will be far too late. Okay. Quantum mechanics is a huge subject. Causality is a huge subject. Taken together, we clearly can't fit them into 45 minutes. So I'm going to have to be selective, and there are certain very interesting issues in the relationship between quantum mechanics and causality, which I'm not going to discuss at all. So, you know that the outcome of particular measurements is unpredictable, and orthodox quantum mechanics says that it's unpredictable in principle. And one question that could raise for a causal account of the universe is how can things which are unpredictable in principle fit into our normal causal understanding of the world, in which A causes B, B causes C, and the chain goes on. I won't discuss this point at all, although it's a very interesting question. The best thing I've ever read on it is actually Mario Bunke's book, which is decades old now, which is called Causality, and which goes in depth into this point. So if anyone is interested, I'd refer them to Bunke. What I've chosen to discuss, though, and what's immediately suggested to the physicist's mind by the title Quantum Mechanics and Causality, is not a clash, as the previous speaker was discussing, between the physical theory of quantum mechanics and philosophical interpretation, but a clash between the physical theory of quantum mechanics and the other physical theory of special relativity. So I'm going to take that as my topic. Because that is my topic, and because I know we have a broad audience, most of this lecture will be introductory. I will describe a lot of what I'm describing using well-worn but roughly accurate analogies. The experts will just have to know in their heads what I mean by these analogies, but hopefully that will enable everyone to follow. And only in the last 5 or 10 minutes will I show my hand, as it were, and let you know where I think the answers to these questions might be coming from, although of course I don't have that answer, because if I did, I'd be in a much larger auditorium and I'd have more money. Okay, so let's start with causality. Actually, of course, interestingly from an historical point of view, the special theory of relativity and the germs of quantum mechanics were being developed in parallel, although largely by different groups of people. But let's start with special relativity and the notion of causation. Why is special relativity a problem for the notion of causation? Essentially, it's because it depends crucially on the fact that the speed of light, which is finite, is the fastest speed at which signals can be passed. We will come back later to talk about whether it's the fastest speed at which signals can be passed, the fastest speed at which energy can be passed, or the fastest speed at which information can be passed. All of these terms were used interchangeably in original descriptions of the theory because it was obvious to people that signals, information, and energy were the same thing. I think in the light of the experiments we'll discuss in quantum mechanics, it will become very obvious that they might at least not be the same thing. We'll have to return to this question of what it is whose propagation is limited by the speed of light. That's a trail in advance. But the essential point is that you can accept that light has a finite speed. Actually, this was measured in the 19th century fairly accurately. But that turns out to have rather deep ramifications for how we have to think about space and time. So the puzzling result is not that light has a finite speed, which we call c, about 12 million miles a minute, but that you might think, therefore, so if I'm walking along at 3 miles an hour, and I throw a tennis ball relative to me at 10 miles an hour, my throwing arm isn't very good, then the speed of the tennis ball relative to the ground is 13 miles an hour. Okay, so I throw it at 10 with respect to me, I was already going at 3, you add these speeds together and you get that the absolute speed of the tennis ball is 13. What's special about light is it doesn't obey that rule. The speed of light is independent of the speed of the source. And that's an empirical fact. So light is special in quite a deep way. It's not just that it has a particular speed at which it's a maximum speed at which it can move. It has this speed at which it always moves, and I cannot alter that by changing the speed at which the source of light moves along. Even if the source of light is moving itself at 99% of the speed of light, the observer sitting on the source of light has to measure the light beam going at the speed of light, and I, watching this person whiz past me at 99% of the speed of light, also have to measure the light beam going at the speed of light. Now, unless we disagree on our yardsticks and our clocks, there's no way that we can both measure that light beam going at the same speed, and so it follows immediately from this empirical observation, plus the requirement that, there's nothing privileged about me compared to the observer sitting on the light source. It follows immediately from this that different observers must disagree about measurements of time and measurements of space. And that's really where the world of relativity gets weird. Moving clocks run more slowly. If my twin goes off in a rocket and comes back later, my twin will be younger than I am by some substantial amount. You worry that that's asymmetric, don't worry. The twin paradox is completely resolvable. There's one of us had to turn round and there's an objective physical fact about who that was. But that gets us then into the question of what happens to traditional notions, and in particular I want to think about the traditional notion of simultaneity, once we realize that different observers disagree about time, have to disagree about time. And the answer is that simultaneity becomes relative. Two events which are simultaneous for a particular observer in this theory are, and in fact, I think we can safely say, are not simultaneous for an observer who is moving at a different speed. So the question, did these two things happen at the same time, is no longer a meaningful question. Unless they're in exactly the same place, but typically they're not. So if the time difference is large enough that one event could have sent a light beam to the other, then we can meaningfully say that the first event is before the other. Conversely, if they're sufficiently the other way around that this event could have sent a light beam to this one, then we can say that this one is before this one. But if they are space-like separated, as the saying is, that is to say they are separated by a distance such that neither could get a light beam to the other, then there is no meaning, if we take this reasonably ontologically strong view of relativity, there is no meaning to say that one of those events happens before the other. Different observers will disagree, but it doesn't matter, because these events can't be causally connected anyway, because they're too far apart to send light beams between them. So this relativity of simultaneity is philosophically disturbing, perhaps, but it doesn't have any nasty consequences for the way in which causation works, if you assume that causation is all carried by light, or by things that move more slowly than light. Okay. So that's the background from the special theory of relativity. Simultaneity is relative, but we get away with this because causal influences propagate at light speed or less. Now let's come to the quantum mechanics, where I'd like to discuss an experiment which, on the face of it, seems to show some kind of causal influence propagating faster than light. This, I think, is a worry. And it doesn't matter whether you're a dualist or a monist or a Leibnizian monadist. Actually, probably if you're a Leibnizian monadist, you don't worry about anything, do you? Pre-established harmony, it's all fine. But if you have a philosophical position that permits any kind of worry, I think you should worry about this. So, in the next 10 minutes or so, I will describe in detail the experiment I think you should worry about. I want to be quite forensic in discussing why you should worry about it, because again, this is an experiment which is often misinterpreted, and things which are not really quantum mechanical phenomena are presented as the interesting bit, when they're really not the interesting bit. And then I want to, having illustrated what the problem is, I want to talk in the last 10 or 15 minutes about what the solutions to the problem might be. If you still think there's a problem by that stage, which some people don't, but I don't understand that. Okay. So, the kind of experiment I'm going to discuss relates to the issue of entanglement that was raised by the previous speaker, namely it involves two particles whose quantum states are somehow involved with each other. And this was, I mean, obviously people have written down things like this before, but the philosophical import of this was first discussed really by Einstein, Podolsky, and Rosen in the famous EPR paper of 1935, Can quantum mechanical description of physical reality be considered complete? A title that to me has always seemed to be missing an article. But that's what the title is anyhow. But I'm not going to describe the experiment as Einstein, Podolsky, and Rosen described it, because there are experiments which are easier to understand and easier to describe, which encode basically the same physical problem. So I'm actually going to describe a more modern version of the Einstein, Podolsky, and Rosen experiment, and I mention this just in case anyone reads the EPR paper and thinks that this is a massive fraud. That rest assured that, to the best of my judgment, the physical content of the experiment I will describe is basically the same as that discussed by EPR. And I'm going to be quite specific about the physical experiment, because I think in general one should be specific about physical experiments. So I'm going to take an atom of some sort. Calcium does this, but various others do it too. And I'm going to excite that atom by heating it or shaking it or whatever. And in the process of de-exciting itself, it is going to emit a pair of photons, quantum particles of light. I'm going to use particle language. Obviously, bear in mind the previous speaker's exhortation that you shouldn't take it seriously. We haven't solved the wave-particle problem, but let's just say that it's going to emit 2 photons, and we'll critique that assertion later. Now, photons are quantum particles of light. Light is an oscillating electric wave, more or less. I mean, it has a magnetic component, but that's very small. So, an oscillating electric wave can be discussed by the plane in which it oscillates. Right? So if the electric field is oscillating, then the oscillation could look like this. It could be going from floor to ceiling, or it could look like this. It could be going from me to you. And that property is called polarization. Okay? So even for ordinary classical light, there are different possible polarizations which tell you the orientation of the plane in which the electric field is oscillating. So let's call this horizontal polarization and this vertical polarization. Which polarization you get, of course, depends on how you generate the light. If you have a vertical antenna, with the electric charges sweeping up and down, it won't surprise you to know that you get basically vertically polarized light. If you have a horizontal antenna with the electric charges zinging back and forth side to side, you get horizontally polarized light approximately. There are other polarizations where the plane of oscillation rotates as you move along the beam, and those are called circular polarizations, and obviously then the plane can rotate clockwise, which is called right circular polarization, or anti-clockwise, which is called left circular polarization. Whichever way you cut it, there are two possible polarizations. If I combine vertically and horizontally polarized light, then I can get one of the circular polarizations, depending on exactly how I do the combination. If I combine left circular polarized light with right circular polarized light, I can make horizontal or vertical, depending on how I do the combination. And if this seems reminiscent of the discussion about superpositions, that's not an accident. Right? So this superposition and the fact that circular is a superposition of linear, but linear is also a superposition of circular, is present already in the classical theory of light. It just gets carried over into quantum mechanics more or less unchanged, because the classical theory of light is also linear. So these properties of polarization get carried on into quantum mechanics. So when we talk about photons, those photons also have a polarization, and I can resolve that polarization into how much vertical and how much horizontal there is, or I can resolve it into how much right circular there is and how much left circular there is, depending on the measurement I intend to make. Now the interesting thing is that because the original atom is not rotating, if one of the photons that comes off is right circular polarized, the other one has to be left. Because the total amount of rotation has to be zero, because there was none there to start with, and there's a conservation law in this game. So that's a physical mechanism by which we generate these entangled pairs. Right? So in the quantum description of this experiment, when the atom decays and emits the two photons, they are in an equal superposition of the first photon being left polarized and the second one being right polarized, and, on the other hand, the first one being right polarized and the second one being left polarized. And so, as the previous speaker was discussing, we're now in one of these weird entangled states where the polarization of each photon individually is not definite. However, it is definitely the case that if the first photon is left polarized, the second one is right polarized, and vice versa. And this is something which quantum mechanics contains very naturally, but which is a strange thing from the classical point of view, namely the existence of definite correlation without definite values. So in entangled states, we know that the polarizations are perfectly anti-correlated, even though we don't know what either of them is. Right. So now the two photons naturally come off back to back to conserve momentum, and so all we have to do is not let them hit anything, and they proceed through vacuum some distance, more often through optical fibers some distance, until they reach two observers. It's conventional to call these observers Alice and Bob. That's admirably gender balanced, but it's a bit Western specific. So my observers are going to be called Ahmed and Barbara. And they are distant from each other, and they make their measurements at very nearly the same time. They've synchronized their watches, they've gone over to their measuring devices, and of course you will understand from the prior discussion of relativity that the point of this is that the measurement events are going to be space-like separated. They're going to be so close to simultaneous that Ahmed could not send a light beam to Barbara after conducting his measurement in the time before she conducts hers. Okay. So the measurement events have this property that whether they are simultaneous or not is observer dependent, and indeed some observers will see Ahmed making his measurement before Barbara makes hers, and other observers will see Ahmed making his measurement after Barbara makes hers. And in terms of how we quantum mechanically describe what's happening in this measurement, that observation is going to be very important. Okay, what is the measurement? Ahmed and Barbara both have a polarizer, and the polarizer measures well, the polarizer, when the photon arrives, either lets it through or doesn't. And it lets it through based on how close the plane of polarization of the photon is to the direction of the polarizer. So if the planes match perfectly, then the photon definitely passes. If the planes are 90 degrees apart, the photon is definitely absorbed. Anywhere in between, according to quantum mechanics, different things happen for different photons, and we can use the formalism of quantum mechanics described in the previous talk to predict how often the photon will pass through. A couple of reference values, just so you know. So if the difference in angle is 0, then the photon will always pass through. If the difference in angle is 30 degrees, it will pass through 3/4 of the time. If the difference in angle is 60 degrees, it will pass through 1/4 of the time. And if the difference in angle is 90 degrees, it will never pass. This is assuming a perfect detector, which we'll go back and discuss later. Okay. So what happens? Ahmed sits by his measuring device. These photon pairs get spat out every 5 seconds or so. And every time a photon is due to arrive at the apparatus, Ahmed notes a 1 if it goes through, and a 0 if it doesn't. Ahmed's results are a random string of 1s and 0s. As you would expect, because the photon that's going to Ahmed is in a superposition of the two polarizations, and so it is as likely as not to have the polarization of the polarizer, and so Ahmed gets a string of numbers which are indistinguishable from the results of tossing a coin and writing a 1 if you get a heads or a 0 if you get a tails. This has been tested, by the way, that these really do pass tests for randomness. The results don't cluster, they do exactly what a tossed coin would if it were perfectly unbiased. Barbara, at her apparatus, is doing exactly the same, and she also gets a string of 1s and 0s that passes any local test of randomness she cares to make. They do this for 20 or 30 photons, or 2,000 or 3,000 photons, and then they go and meet for coffee, and they compare their lists. And they see that wherever Barbara has a 0, so wherever the photon did not pass her apparatus, Ahmed has a 1, and wherever Ahmed has a 0, Barbara has a 1. And that's the perfect correlation. So that is evidence of perfect correlation between space-like separated events. Is this a problem for relativity? Show of hands. Hands up for yes, this is a problem for relativity. Hands up for no, this is not a problem for relativity. Hands up for not putting my hand up to either of the previous two. Good. Sensible abstinence. So, not one of my personal philosophies actually, but so my claim is that this by itself is not a problem. At least in terms of the worry that Ahmed could signal to Barbara faster than light using this correlation. It may be a worry for other reasons, so I'm not saying that the people who answered yes are wrong, they may just be further ahead. But for the simple worry that Ahmed can signal to Barbara using this system, that is not a concern. Because Ahmed would have got exactly the results he got if Barbara had been taken out in a large nuclear explosion near the beginning of the measurement series. Similarly, Barbara would have got the results she got if Ahmed had been taken out, or at least she would have got results that were statistically indistinguishable from them. So there's no way that Barbara can tell from doing her measurements that Ahmed is there at all. And there's no way that Ahmed can tell from doing his measurements that Barbara is there at all. The correlation which seems to have been present only becomes apparent to either Ahmed or Barbara when they bring the results together, and of course, as they're written on paper or contained in a laptop or something, this has to be done below the speed of light. So this is fine. It doesn't violate relativity in the obvious way. This is not a signaling mechanism. And you might think, oh well, can I invent something clever that uses this to signal? No, you can't. At least there is a no signaling theorem that I don't see a hole in that says that you can never signal from A to B faster than light using the existence of these correlations. So, let me make one more comment on this, which is that actually what I've described so far has nothing to do with quantum mechanics. So, Ahmed and Barbara had their polarizer set at the same angle, so they were measuring in the same plane. And we know that if they do that, one particle will pass and the other will not, we just don't know which. There was a cartoon shortly after the initial discussion of this, and I forget who the cartoonist was, and I'd be very grateful if anyone in the audience knows and could remind me. I've been looking for this for years, but I swear I once saw it in the same dream where the snakes ate their tails. And it's called Bertelsmann's Socks. And it's about Professor Bertelsmann, who always comes into the university wearing odd socks. And he only owns red socks and green socks, which means that if you see a red sock on one of his feet, then there'll be a green sock on the other, and you can know that without looking. But obviously he puts them on randomly, and so you don't know which foot the green sock is going to be on. But you always know there'll be exactly one. Now, this reproduces perfect anti-correlation between the results of colour measurements on the 2 feet. You could take the feet and separate them to a space-like separation, although this would be uncomfortable for Professor Bertelsmann, and you would still have perfect correlation. But there's clearly nothing quantum mechanical about this. So the point is that entanglement produces perfect correlation, but perfect correlation is not evidence of entanglement. We can achieve perfect correlation in completely classical sock-based ways. However, the quantum mechanical correlation emerges and becomes distinctively quantum mechanical when Ahmed and Barbara start to rotate their polarizers so that they're measuring in different planes. And here the predictions of quantum mechanics really do seem to become inconsistent with the results of the idea that the 2 photons have somehow already decided their polarizations before they set off. Because remember, the quantum mechanical prediction I explained, that if the polarizers are at the same angle, then the results, well, you should get perfect anti-correlation all the time, which means the results in this experiment, the results should disagree 100% of the time. But if I separate the polarizers by 30 degrees, the results should disagree 75% of the time. If I separate the polarizers by 60 degrees, they should disagree 25% of the time. And if the polarizers are 90 degrees apart, then in fact Ahmed and Barbara's results will always agree. So they will either stop both photons or they will let both photons through. And it's this fact that the quantum mechanical prediction depends only on the relative angle of the polarizers, which is something that neither of the photons ought to be in a position to know, which is where the strange correlations come from. Now, for those not used to thinking about polarizers, I'm immensely grateful to Tim Maudlin, who in his book on this topic creates a very understandable analogy of the problem. So in this analogy, you and a friend of yours are going to be the 2 photons. This lecture theatre is going to be the atom, and outside this lecture theatre is going to be the rest of the laboratory. So you and your friend are shut in this room, and you're told you can develop whatever strategies you like, but when you leave the room by separate doors, you must then not communicate with each other. And when you leave the room by separate doors, each of you is going to be asked a question, and that question will be in the form of a number, 0, 30, or 60. Obviously these represent polarizer angles, but you don't have to know. When asked that question, you have to say yes, which means you pass through the polarizer, or no, which means you don't. So far, so good. However, the rules are, as set by quantum mechanics, if you and your friend are asked the same question, you have to give the same answer all the time. If you and your friend are asked questions that differ by 30 degrees, you have to give the same answer 75% of the time. And if you and your friend are asked questions that differ by 60, you have to give the same answer a quarter of the time. And it's not hard to show, and it's proved in Maudlin's book algebraically, but the best thing is to try. It's not hard to show that there is no strategy whatsoever that you and your friend can cook up that will allow you to comply with these rules. And the reason why not is that the rules are based on the relative angle, and you won't know the relative angle. And you don't have enough freedom to hedge. Right? There are too many possible questions for you to invent a strategy that will work in all cases. So this is a cartoon version of a result first solidly established by Bell, who's already been mentioned, I'm pleased to say, published in 1963. I think there's evidence it was established rather before that, which places limits on the correlations that there can possibly be between independent particles which have made their decisions before leaving the atom. And the predictions of quantum mechanics surpass those correlations, which is what I mean by saying that you cannot agree anything with your friend locally that will allow you to obey the quantum mechanical rules. Of course, in the quantum mechanical description, this isn't a problem, because the quantum mechanical description doesn't require you and your friend to reach any agreement before leaving the lecture theatre. The quantum mechanical description is quite happy with the idea that while the two photons are propagating, they are in this entangled superposition. And according to the measurement postulate, at the point where Ahmed measures the polarization of the first photon, the wave function of the other collapses from the superposition into whatever state it was that Ahmed didn't measure. Which sounds fine, until, so we just say, okay, there's wave functional collapse, and Ahmed's measurement has collapsed the wave function, which means that the outcome of Barbara's measurement is now predetermined for the nanosecond until the photon reaches her device. But now recall the discussion of relativity. These measurements are space-like separated, so there is no physical meaning, according to relativity, in describing the order in which they happened. That means that for me, an observer standing still in the laboratory, Ahmed makes his measurement slightly before Barbara makes hers, but there are other observers in the world going past on trains or something, always trains in relativity, although they don't move very fast, so the time dilation's tiny, but some very quick train, foreign train. And for that observer, Barbara makes her measurement before Ahmed makes his. So the account I give of what happened in orthodox quantum mechanics with the measurement postulate is that Ahmed measured the polarization of the photon coming towards him. That measurement induced collapse of the wave function. Because of the collapse of the wave function, the photon approaching Barbara went into a definite polarization state, which Barbara then measured. The observer on the train, on the other hand, says that Barbara made her measurement first, and because of her measurement, the wave function of the two photons collapsed, well, the remaining photon, and the state of that photon now became predetermined. And then, therefore, Ahmed just measured what the state of that photon was. Now, if you're a hard-line positivist, there is no contradiction, I think, in what I've just said. Because as far as any observable thing goes, the observer on the train and I would predict the same thing. We would both predict that at the end of this run of experiments, Ahmed and Barbara would each have a string of ones and zeros, and when they brought them together, they would be perfectly correlated if they had their polarizers the same, 75% if they were 30 degrees apart, and so on. But I think you don't have to be an extravagant metaphysicist to think that there's something a bit funny in the fact that different observers disagree on who it was who collapsed the wave function. So I think one place where there is certainly a tension between quantum mechanics and special relativity, or at least between the orthodox account of quantum mechanics and special relativity, is in this area of collapsing the wave functions of multiple entangled particles where the collapse event is space-like separated from the subsequent measure. Okay. So that's explained the question, and I think, Simon, I've got about 10 minutes? I think we started at about 25, so let me take 10 or so. Okay. So there are various responses to this which I would call Weasel responses. And it's hard to say that without sounding like you denigrate the people who make them. Let's say they are the class of responses that I am pretty sure will eventually be ruled out by experiment, possibly in the fairly near future. However, I will mention them because they are current, possible live responses to the problem. And they are the responses that say, okay, the experiment is imperfect. So the experiment I described has been done many times. I'm particularly fond of the version that Alain Aspect did in 1981, but there are various refinements that have been done on it. But that process of refinement is not at an end, and there are still loopholes. One loophole, for example, is the detection loophole. So if I actually do this experiment with light, I cannot make detectors that are as good as the ones I've described Ahmed and Barbara as having. And in fact, I can't even get very close to making detectors that are that good at the single photon level, which is what we need. So there remains the possibility that although the subset of measurements in which both detectors fire, i.e. the subset of measurements which are ideal in the way that I need, I see the predictions of quantum mechanics borne out, it may be that they are an unfair sample of the total number of photon pairs, and if I sampled the complete set, then I would find that the correlation subsided back down to the classically predicted levels. Now, I can't disprove that possibility, but I don't believe it for a moment. The reason I don't believe it is because if the sampling were unfair, we should have seen some variation in the unfairness of the sampling in the different runs of the experiment, which were done on different kit. And we don't see that. We see things systematically approaching the quantum prediction as the detector devices are made more and more sophisticated, and as they get closer and closer to the ideal limit. I am confident, although this is pure personal opinion, I'm confident that that detection loophole will be closed, and that when it is closed, we will still see the particles obeying the quantum mechanical prediction and not the classical one. Another loophole is, of course, that there has been plenty of time for the information about the angle to which Ahmed set his polarizer to get across to Barbara's experimental station, and vice versa. Because typically you set the experiment up, you pump out the vacuum tubes, you spend some time getting everything ready, and then you set it going, and clearly at that point, the event where you set the polarizer, which is really all the other photon needs to know, is in the past of that photon and it has access to it. So there are also these explanations that say, well, the measurement events themselves are space-like separated, but the information about what the polarizer is set to could easily have got to the other experimental station. Now, you can do experiments to rule this out, or at least to make it very implausible, because it is possible to get the polarizer to set itself randomly after the photons have already started their journey. And versions of this experiment have been done where the polarizer is randomly set a microsecond or so before the measurement takes place, so that, it seems, information about the polarizer setting can't get to the other side of the system. But those experiments have only been done with photons, where you have the detection loophole. So one could still claim that in the experiments done with photons, we're getting the quantum results only because of the detection loophole, and if the detectors were made better, things would subside to classical. And in the experiments done with massive particles, where we haven't done the rapid polarizer setting, we're getting the quantum results only because the setting of one polarizer is in the path light code of the other. I cannot disprove either of these statements, but I'm against global conspiracies. I don't mean I'm fighting them, I mean I generally don't believe they exist. And this seems a bit of a conspiracy. So I'm fairly confident that when all this is cleaned up, we will have experiments with massive and massless particles, both of which show the predicted quantum correlations, and these loopholes will be closed. Assuming these loopholes are closed, what could the answer be? Well, I'm going to stick to answers that I know how to do a calculation for. Which doesn't mean that there aren't other answers, it just means that I'm insufficiently expert to speculate what they might be. There are, of course, answers out there in the literature that involve departing from the traditional interpretation of quantum mechanics. I suspect that in variants of the many worlds interpretation, this problem ceases to be a problem because everything's just going into superpositions, and that relativity doesn't tell you about the order in which parts of the universe have to go into superpositions with each other, so probably in many worlds this is all okay. I have my own problems with many worlds, which I'd be delighted to discuss in the panel this afternoon, but they don't really belong here. So let me point out one thing, though, which does trouble me about the way I framed this argument and the way that everybody frames this argument. And that is that when describing the evolution of the photons, we almost invariably use non-relativistic quantum mechanics. So there is a version of quantum mechanics that is compatible with special relativity, but you discover that to make quantum mechanics compatible with special relativity, you have to include various possibilities. And one of the possibilities you have to include, for example, is the possibility of particle creation. Right? You all know that when we hammer these two particles together at CERN, about 100 particles come out. So in relativistic quantum mechanics, the number of particles is not conserved. Now, if the number of particles is not conserved, you might worry about my statement that the atom, when it decays, emits exactly 2 photons. Also in relativistic quantum mechanics, there's no obvious simple local operator that measures the polarization, which means that the calculation I do in non-relativistic quantum mechanics to predict what correlation I should see does not carry over in a completely straightforward way into relativistic quantum mechanics, or, well, quantum field theory as it should be. And the third issue is that in relativistic quantum mechanics, quantum field theory, space is not empty. So in quantum mechanics, the vacuum itself has fluctuations. And the calculations that have been done on this matter show that at the very least they change the question you want to ask about the relative state of Ahmed's detector and Barbara's detector. And there are some interesting, tantalizing results, which I haven't worked through in full detail, about the relationship between dephasing of vacuum fluctuations in the quantum field and what you would expect for correlations between distant measurement events. So that's not an answer to the problem, but it is a salutary warning. And in this sense, although I don't agree with Hawking's quotation, I can see what he's trying to say. One shouldn't refuse to base philosophical interpretations on simplified versions of theories. Often that's a very enlightening thing to do. But when one starts to get evidence that the complicated version of the theory actually changes the description of the phenomenon compared to the simple one, then one should certainly be cautious. And I think over the last 10 years, and I have a few references here for anyone who'd be interested in them, I think hard calculations in quantum field theory are starting to suggest that conceivably what's wrong with our attempt to interpret the EPR experiment is not the relativity, but the simplistic, non-relativistic way in which we're describing the quantum mechanics. That's not an answer, but as was discussed earlier on, it's an indication of a possible set of questions. And Tomasini and Kaban and Rebulinsky and Lin and Hu over the past decades and many others have been working hard on trying to see if you can even formulate the EPR problem in an exact and agreed way in the relativistic theory. This matters, of course, because in non-relativistic quantum mechanics, the speed of light is infinite, and so none of these problems arise. So in a certain sense, what I've done in this lecture is smoke and mirrors. I've taken a problem described in a theory which takes account of the finite speed of light, but no account of quantum phenomena, and I've faced it with a prediction from quantum mechanics which takes account of quantum phenomena, but no account of the finite speed of light. And that, I think, leaves open the possibility that there is a route to the solution of this problem within physics, which doesn't require, or may not require, significant rewriting of the orthodox interpretation of quantum mechanics, although I'd be very interested to hear people's views about that. Okay, I think that's all I have to say. Thank you very much.
Because this would persist even in the relativistic quantity.
Yeah, I mean, I'm inclined to say yes. And the reason I'm inclined to say yes is because of experiments like scanning tunneling microscopy, or for that matter, cutting a diamond crystal into facets, where we pretty much directly observe the wave function. However, saying that something's real doesn't mean that it's the right language in which to talk about the system at all energies. So, in the same way that, a table is real, but if I heat the room to 10,000 centigrade, a table will rapidly cease to become the right description of what's going on in the room. And a wave function could, in my philosophical approach to these things, a wave function could simultaneously be real and be an inappropriate description above certain energies and speeds.
Do you have any questions?
Thanks, Chris. So this is a question about the role of causality in our understanding of space-time structure. So it's well rehearsed in the literature, at least in the philosophical literature, I would say, and I assume in the physics literature, that you can reproduce most or all of space-time structure, relativistic space-time structure, by beginning with nothing other than some kind of a causal relation on the points of space, some kind of a partial ordering. However, if I'm not mistaken, you can also axiomatize, say, in Minkowski space-time, in terms of primitives that don't include any kind of a causal concept. So, if that's the case, I'm curious to hear from you how strongly you feel that we do have to take causality as some kind of a primitive when we talk about relativistic space-time structure, and then, to what degree your answer determines whether the situations you've been describing really pose any problems with relativity.
Excellent question, thank you. So I can answer the first part very straightforwardly, I think. From the pure point of view of formulating the theory, we don't require causality. And in a certain sense, the picture offered to us by special and general relativity is a picture which is more comfortable without causality. In the sense that, what does it say? It says there is this manifold, Minkowski space or Riemannian space-time in the GR sense, and events are located on that manifold where they have coordinates. And the manifold is supplied sort of once and for all time, and so it's just a painting. You don't look at the garden at Giverny and wonder if the lady is causing the tree or the tree is causing the lady. It's just a painting. So that's fine, except that it seems wrong. And it seems wrong because we have day-to-day experience which seems not really to fit causal explanation, but not to fit non-causal explanation. Now, maybe the right answer to that is to say, okay, our minds have this property that they stamp causation on things, and they have this property that they stamp space on things and time on things, so what? The physicist doesn't need to care about that. But that just seems unsatisfactory. And I can't say better than to say that it seems unsatisfactory. So there seem to be such clear examples of causation. There are two. That I don't want my description of the world to say that that was preordained and all that actually... I can't make sense of my role as observer if I don't have causation. For my role as observer, I need tensed time. Even though modern physics doesn't naturally throw up tensed time, apparently. If I have tensed time, then I pretty much have to have causation. So I think it's not so much that causation is forced on us by the metric structure, it's forced on us by a desire to map the metric structure onto our actual experience of experiments. Rather in the same way that wave function collapse is not forced onto us by the Schrödinger equation, it's forced onto us by our desire to map the Schrödinger equation to what we actually seem to see in the world.
Any other questions?
You mentioned in the relativistic formulation of this that there are particle antiparticle pairs which can be produced, so there's a potential for more photons than the two.
Can you use the microphone, please?
You mentioned in a relativistic formulation that there's more than one. There might be more than one pair of photons And I was just wondering whether there was any way in that case that ARPANET could be sure that the photon that he was detecting was the one that came from the original pair production, and if there was a way of labeling the photons so that he could be sure whether that might disrupt the results of the experiment.
Thank you for that question. So, this is actually a thornier issue with photons than it is with other particles with which we might do the experiment. So if you'll forgive me, I'm going to answer your question for other particles and then explain why photons are a problem. If I did the experiment with electrons, and I use their spins as the thing that gets correlated, I know that the electron has a mass, and so I know that to create two other real electrons that leave the system, I need an energy of at least 2 electron mass times c squared. So in that case, I could just guarantee that there wasn't that energy density anywhere in the system, and then I would know that although I had virtual fluctuations where electrons and positrons were created en route, they could not actually develop into real electrons and positrons leaving the system at some other angle. So then I'd be okay, because I would know that anything that arrived at Ahmed or Barbara's measuring device must be one of the 2 real electrons that was created at the source. The problem with doing that for photons is that they don't have a mass, which means that there's no threshold of energy below which you can guarantee not to create other photons. The way we guarantee not to create other photons is that, as far as we know, there is no physical process by which one propagating photon can turn into 3 without the presence of an active medium, such as a crystal. So the way we guard against creation of new particles in the photon experiment is actually somewhat different. It's not keeping the energy low, it's keeping the beamline clean. And according to our current theories of these things, if we propagate a single photon through a clean beamline, even in field theory, we are guaranteed to get a single photon out at the end. So, for different reasons, we seem to be able to keep possible actual particle production under control in both of the experiments. I'm more worried about the virtual processes that happen during the propagation of the photon, but which ultimately don't lead to the creation of any new particles. And of course, to answer the last part, you're right that if such new particles were created, labeling them would disrupt the interference.
Any other questions? Is it time? Yeah, okay. That's fine.